f of x, which is x e to negative x squared over 8, and we are given negative 1, 4. So we want max min. We're not asked to graph. All we want is to determine max min, absolute, local, whatever. So I get my table going, and it has to show between negative 1 and 4. So I have to have f prime, and I have to have f of x. I will determine the derivative. It's a product. So then what do I get? So it's a product. When I differentiate x, I get 1. E to negative x squared over 8 plus x times e to negative x squared over 8 times negative 2x over 8. Yes, it has to be simplified, but for now, I'm going to write it like this. Is this okay so far?
So you don't put it in LA since it's hour and 8.
It's e. So do not confuse this with tangent x raised to cosine x. That's a different story. This is a function, this is another function, but e is not a function. E to the x is a function. E is just a number. So when you have e here, e to cosine x prime, it's e to cosine x times cosine prime. Better? Okay. So then I will definitely factor out e to negative x squared over 8. I will have 1, but minus. I will simplify, and I will get x squared over 4. Please tell me if this is okay so far. Is that a yes? Is that a no? Yes? Okay. So then I'll have 4 minus x squared divided by 4e to x squared over 8, or negative x squared minus 4 over 4e to x squared over 8, and of course minus x plus 2, x minus 2 over 4e to x squared over 8. Because I need to set this equal to 0. And when I set f prime equal to 0, what do I get? Equals? Excellent. X equals plus or minus 2. However, negative 2 is outside of the domain, so I'm only interested in 2. I have to study the sign of the derivative. Ready? Okay. I will not study the sign of this. It's a waste of time. This is always positive. So when I plug in 0, which is on this side, 0, then I have positive and then negative with minus is positive. When I plug in 4, positive, positive with negative. Now I have, in the graphing calculator, I have to put the function in because I need to determine these values. When x is negative 1, when x is 2, and when x is 4. So let's do just that. So in y equals, clear if you have anything in there. So I have x, and then e in parentheses, please, negative x squared, divided by, I think it was 8, right? Yes. Close the parentheses. And with the second table, I want negative 1, 2, and 4. Oh, I always forget that this, okay. Negative 1, 2, and 4. So with negative 1 is negative 0.89, negative 0.9. With 2 is 1.2, and with 4, 0.54, 0.5. It's good enough. So now I check whether these two rows work well together. This is how I check, or how I catch my mistakes, I should say better. From negative 0.9 to 1.2, yes. From 1.2 to 0.5, yes. So I will say that this point is definitely a absolute min. This point 2 comma 1.2, not with 0, 2 comma 1.2 is definitely absolute max. And 4 comma 0.5, nothing. Any questions on this problem? Any questions? Please don't forget to finish your work in WebAssign, please. The test on Wednesday. On a graph like this, then I'll take your next question. On a graph like this, for example, we're asked to find the absolute max and local max, and max, min, absolute, and local. So obviously this point doesn't mean anything because first of all, it doesn't even exist. Now this one, because all function values are higher left and right, and I can show the open interval, this will be a local min. So at 2 comma 2 is a local min. This one is a local max at 3 comma 4. This one is a local min at 5 comma 1. This one is a local max. This one is also an absolute min because there is no other value smaller. And this one is nothing. Local max, local min, absolute min, and also local min. Now, if this point, imagine that this point is not here. I don't want to, I do have my pencil. Anyway, but just imagine that this point is not here, but here. Not here at all, but up here. That will not be a local max because the function value left and right are not smaller, are not, actually, this is a local min because the function values are higher. So if the value is here, that will be a local max as long as I show that the function, yep, it will be. In that case, if it's up there, it will also be an absolute max. But right now, there is no absolute max. Okay. Any questions? Okay, your next question, please. Your next question. Next question, please. Anything else you want to continue with?
mean value here?
The mean value theorem, very good. Do we have one here? Is it? Very good. Thank you very much. So we have negative 2, 2, and f of x equals x cubed minus 3x plus 2. Thank you, Carl. So we're asked to show whether on the theorem, the mean value theorem is applicable here. And if it is, to find that C, at least one, that comply with a given. I'm losing my voice, I'm sorry. That complies or is guaranteed, minimum one C guaranteed by the mean value theorem. So first I have to write that f is continuous on negative 2, 2. I have to write that. And I have to say why as a Pauli function. Number 2, I have to write that f is differentiable at least on the open interval. I don't care for more. And then I have to say that there exists a C in the open interval negative 2, 2, such that f prime of C equals f of 2 minus f of negative 2 over 2 plus 2. Guaranteed by MVT. Guaranteed by MVT. So, find f prime of x first as 3x squared minus 3. Plug in C and write C, 3c squared minus 3 equals. Find f of 2, 8 minus 6, 2 plus 2 is 4. And plug in negative 2, negative 8 plus 6. I think I get 0. Correct me if I'm wrong. So I determined f of 2 plugging in the function 2, and I got 4. Let me know if it's correct. I plugged in negative 2 in the function, I got 0, and then 2 plus 2 is 4. So the equation I have to solve is 3c squared minus 3 equals 1, or 3c squared equals 4, or c squared equals 4 over 3, or c equals plus or minus the square root of 4 over the square root of 3, or plus or minus 2 the square root of 3. But I have to show that this is in between negative 2 and 2, because if it isn't, then I made an error somewhere. So with a calculator, I calculate this. So I have 2 divided by the square root of 3. And I got 1.15. So yes, they're both plus or minus. So in this particular case, the theorem showed that 2 such C's are possible. Any questions? I would like to look at 38 on page 281. And then you're next. So we alternate. I pick, you pick. So I'd like to look at 38 on page 281. So g of x equals x to 1/3 minus x to negative 2/3. We're asked to find the critical numbers. 1 minute. Critical numbers, please. put the attendance in and this won't let me. After you left last time, it worked. You were not here, but remember we had difficulties with. Okay, do we have an answer? Did we determine G prime? 1/3 x2, excellent, plus 2/3 x2, 5/3. Okay, perfect. First of all, I will factor out 1/3, and I will also factor out x to the smallest of the two powers. Is negative 2/3 smaller than negative 5/3, or is negative 5/3 smaller than negative 2/3? That's what I have to pull out. So which one is it? Really? Which one? The negative 2/3 or the negative 5/3? Very good. So negative 5/3. And now careful what we get. Ready? So, what is the first term? So from negative 2/3, we subtract negative 5/3. From negative 2/3, I subtract negative 5/3. What is the answer? One. So it's just x. Plus what? Plus 2, indeed. You can always go back and check, right? 1/3 times x to negative 5/3 times x, copy the base, add the exponents. Negative 5/3 plus 1 is negative 2/3. Then you multiply these two, you get 2/3, and you have x to negative 5/3. And that's what you need. So this is x plus 2/3, the cube root of x to the 5th. So when you set g prime equal to 0, what do you get? You could say x equals negative 2 and x equals 0. However, x equals 0 is not a critical number because the function is not defined at 0. Because this will be 1 over the cube root of x squared. So this cannot be considered a critical number. It would have been if the function were defined at 0, but the function is not defined at 0, so this cannot be a critical number. So the only critical number of this function is negative 2. Good, you're next in asking what you want. So we know how to find absolute max min from a graph. We know how to find critical numbers. We know how to find the absolute max min on a closed interval. We know how to apply the mean value theorem, correct? So if I come back to this graph and I ask, same graph, doesn't matter really, any graph. If I ask here, when is this function increasing or decreasing? Very clear, right? It's decreasing between 0 and 2 and between 3 and 4. And it's increasing between 2 and 3. And it's increasing, and also between what, this and this, right? And then increasing and then decreasing. So 1, 2, 3 pieces of decreasing, 1, 2 pieces of increasing. What if I ask when is the function concave up? So it's concave up between 0 and 2, is concave down between 2 and 4, and also concave down between 4 and 7. So it's concave down between 2 and 7. Okay, perfect. You're next to ask anything you want. Okay, I want to look at one more graph. Here it is. Okay, the problem is asking us, this is the function, this is the derivative of a continuous function. On what intervals is f increasing or decreasing? And on what values of x does f have a local max or local min? So we did the same thing with a different graph. So now I have to look for my pencil. I got it. Ready? Ready? So the function is increasing when the derivative, so this is the derivative. So the function is increasing every time the derivative is positive. So between this point and this point, the function must be increasing, as well as between this point and this point, because the derivative is positive. Would you agree? The derivative is negative, so obviously between 0 and 1 and 6 and 8, so the function is decreasing. Agreed? Okay, then we are asked, where does it have a local max? So from negative to positive is a local min. So at this point, it has a local min. The derivative has to be 0 or undefined, and the sequence of signs must be negative to positive for a local min. At this point, at 0, it has a local max because it's coming from positive to negative. At this point, it's coming from negative to positive, so it's a local min. Concave up, concave down. So we have to differentiate this function, right? To determine concavity. So yes, so if the sequence is positive, so if the derivative will be positive or increasing, in other words, then the function will open upward. So this function is increasing between 0 and 2. It's increasing between 3 and 5. And it's increasing between 7 and 9. When it's increasing, its derivative, which is the second derivative now, will be positive. So that makes the function open upward. When it's decreasing between 2 and 3, and it's decreasing between 5 and 7. Then the second derivative, is negative, so then the function is concave downward. State the x coordinates of the points of inflection. So this from increasing to decreasing, this one will be an inflection point. From decreasing to increasing, this one will be an inflection point. From increasing to decreasing, this one will be an inflection point. And then from decreasing to increasing, this will be an inflection point. So 1, 2, 3, 4 inflection points. Any questions? Any questions? Yes? Questions? Okay, your turn. The next topic will be L'Hopital's rule. L'Hopital's rule, graph, Newton's method, and slant asymptotes. There is nothing else. Newton's method, optimization, slant asymptotes, and a graph. What would you like to continue with? What would you like to continue with? Graph, Newton's method, optimization. Yes, L'Hopital's rule. Yes, very good. So those are in 4.4. Any preferences? Page 308. Page 308. Anything you want. Which one? From 15 through 66. We did most of them. We can look at the review at the end, if that is better. It's up to you. You can choose from 308 or from here. I think we covered those too, but it doesn't matter. So these are 7 to 14 on 308. - 15 through 66. Which one? 31? Yes? Yes. Very good. So we picked 31. So let's take a look. 31, I'm assuming 308, right? Right. Okay, 31, 31, 31. Excellent. So limit, x approaches 0 from x, 3 to the x, over 3 to the x minus 1. Good pick. So the first thing I have to do is just plug it in. And I'm always hoping for 0 over 0. So the most difficult situations are powers, right? 1 to infinity, 0 to 0, or infinity to 0. Those are the most difficult ones. Ratios are nice. So it happens that this is 0 over 0. But I have to be very careful because the numerator is a product. So then we have limit as x approaches 0. So we have x times 3 to the x. The first function prime is 1 times 3 to the x, and plus x times 3 to the x prime. So I don't want you to forget this. Just always remember e to the x prime is e to the x. But it should be e to the x times natural log e. But natural log e is 1. So then when we differentiate any other number to the x power, we write 3 to the x but times natural log 3. Just remember, why don't we write natural log e? It's because natural log e is 1. So now the denominator, when we differentiate, we get the same thing. It's just, it's not a product, so we get 3 to the x times natural log 3. Now look at this expression and say, I know what you're going to do next. Or just tell me what. And I'll do it. Yes, of course. 3 to the x from the top with 3 to the x from the denominator, they will hopefully and happily go away. So this is 1 plus x natural log 3. And now I have no difficulties. This is not an indeterminate case anymore. When I apply x approaches 0 at the top, I get 1, and the denominator is natural log 3. And that's it. Anything else?
You said something about slant asymptote, is that correct?
Slant. Slant asymptote or oblique asymptotes. Sure. Can anyone refresh our memory on which functions, which rational functions have slant asymptotes? Only when the degree of the top is by exactly 1 unit higher than the degree of the denominator. Very good. So let's pick on page 318. Problems 61 through 70, they all have slant asymptotes. 61 through 70. Yes, which one? Okay, I will choose 62. 62, we have 2x cubed plus x squared plus x plus 3. Everything divided by x squared plus 2x. We're asked to find the slant asymptote. First of all, does it have a slant asymptote? And the answer is yes, because the degree of the top is 3, the degree of the denominator is 2, so it has to be, the quotient will be a line. Good. There are no missing terms. They are in descending order, so we can start. 2x cubed plus x squared plus x plus 3, x squared plus 2x. And I'm ready when you are. Ready? Remember, the quotient has to be a line. So x squared times what is 2x cubed? And the answer is 2x. We go back and distribute. Negative 2x cubed plus 4x squared minus 4x squared. Negative 3x squared and plus x. X squared times what is negative 3x squared. Indeed. Negative 3 times x squared is negative 3x squared, but positive 3x squared. Negative 3 times 2x is negative 6x, but positive 6x. I can continue. I don't have an answer. X squared times what is 7x? I can't. So then this function can be replaced by, can anyone tell us by what? Right? 2x minus 3, but plus what? Yes, 7x plus 3 over the denominator or the divisor. Only this piece we're interested in. Why? Because when x approaches infinity, this will approach 0. So the slant asymptote is y equals to x minus 3. And the end behavior of the slant asymptote is the end behavior of the function. What is the end behavior of 2x plus 3? Is it this? Minus 3. Is it this? Or is it this? Right, this one. So that's what the function is going to do. It has to follow the slant asymptote. So it's coming from negative infinity going to positive infinity. Good. Is this okay? Good. So only rational functions with a degree by 1, exactly by 1, higher in the numerator than the denominator. So that the quotient is a line. Otherwise, the quotient will not be a line. Only when we divide degree 3 by degree 2, we get the quotient to be a line. If we divide degree 2 by degree 2, we do not get a function. I mean, we do, but we get a horizontal line. Okay? And if we divide degree 4 by degree 2, it's not going to be a line. Good. Next question. Anything else? Are we okay with Newton's method? Are we okay with graphing? Yes, let's do a graphing problem. So we know what happens when a factor goes away. The domain has to be stated before. And then when it goes away, what happens? Okay, so would you like to work on a rational function? Yes? Okay, rational function it is. Do you want to work on it for a couple of minutes or not? It's okay if you say no. I'm not lazy. Okay, so 22 on page 352, y equals x over 1 minus x squared. So the problem will ask you to go over everything. Asymptotes, domain, x and y intercepts, inflection points, max, min, x-intercepts, of course, y-intercept, of course. If anything exists, we have to determine it. So you want me to start, or you want me to wait for a couple of minutes? You want to wait? You want me to start? Okay. Yes? Okay, perfect. So here's what I would do first. I don't like negative leading coefficients. I don't like anything that is not presented in descending order. And I will immediately write this. Because that tells me immediately what the domain is and what the x-intercepts are, if they exist. So now I will get my table going. I will have f prime. I will have f of x and f double prime. I know that this function is not defined at 1 and negative 1. And if the function is not defined at 1 and negative 1, its derivatives cannot be defined there. So I will write immediately negative 1 is a VA and 1 is a VA. Is this okay so far? Yes? I can also say that this must be 0. When I plug in 0, I get 0. I can also say that this must be 0 and this must be 0. Why? Because the degree of the denominator is bigger than the degree of the numerator. Let's say we don't know that. So then I have to show that limit as x approaches negative infinity from x over 1 minus x squared is whatever. So right now it's infinity over infinity. I know L'Hopital's rule. So limit as x approaches negative infinity of 1 over negative 2x. And now I know for sure that this must be 0. Because the numerator goes to 1 and the denominator to infinity. So I differentiate to the top, I got 1. I differentiate the denominator, I got negative 2x. So it must be 1 over 0. 1 over infinity, which is 0. So then I write y equals 0 is a horizontal asymptote. I need to determine these. And determining the limits left and right will tell me where the function is going left and right of the vertical asymptotes. So I have to find the limit as x approaches negative 1 from the left of negative x over x plus 1, x minus 1. And the same from the right, and the same from the left of 1, and the same from the right of 1. Is this function symmetric before we continue? Because if it is symmetric, then it would be easier to determine. I don't have to write all these limits. When we replace x by negative x, we will get the opposite of the function. So let's do that before I continue. So the function is negative x over x squared minus 1. And when I determine f of negative x, nothing changes in the denominator, but the negative and the negative become x over x squared minus 1. So this equals the opposite of the function. When this happens, what type of function has this property? That f of negative x equals negative f of x. Odd function, very good. So it will be whatever the graph is, must be symmetric with respect to the origin. Excellent. Okay, so we haven't finished the limit, so we're continuing with the limits. So I know that the numerator is with negative 1 is positive, and I know that the denominator is 0. So I know that the answer must be an infinity. I don't know which one. So with negative 1.1 to the left, negative, negative, negative. So the result must be very good. So I think that this is positive infinity. We'll catch our mistakes immediately. If this row doesn't work with this, then I know, oops, something is terribly wrong. Okay, so let's determine the limit from the left of negative 1. I'm sorry, from the right, of course. This was from the left. So limit as x approaches negative 1 from the right, from a negative x over x plus 1, x minus 1. So whatever it is, the numerator is positive, but the denominator is 0. So negative 1 from the right is negative 0.9. Negative, positive, negative. I see this time 3 negatives. So the answer would be negative infinity. Very good. So then I know on this side we have negative infinity. If that's the case, these have to be reversed. Otherwise the function will not be odd. But let's check. So from the left of 1. So limit as x approaches 1 from the left, from negative x, x plus 1, x minus 1. The top is negative, the bottom is 0. So this must be an infinity. We don't know which one. One from the left is 0.9. Positive, positive, but negative. With 0.9. Positive, positive, negative, but there is a minus in front. Yes, it is. Indeed. As expected. Otherwise, it would not be symmetric with respect to the origin. Since we determine all of them, let's determine the last one. So limit as x approaches 1 from the right from negative x, x plus 1, x minus 1. I know again it's negative 1 over 0, so it must be an infinity, but I need the sign. With 1.1, positive, positive, positive. Negative indeed. As expected, negative infinity. So this is completely done. We can't find anything about the function from the function itself. Okay then. Then I have to determine the first derivative and then the second. Now when I determine the derivative, I prefer this, not this. Of course, this. So I'm going to copy y, negative x over x squared minus 1. And then y prime, negative, the ratio, the top prime is 1, x squared minus 1 minus x times the denominator prime over the denominator squared. Is this okay? Okay, so let's see what we get. Negative x squared minus 2x squared is negative x squared and minus 1 over x squared minus 1. I like this very much. So, are there critical numbers? Are there critical numbers? Critical numbers come from two possible sources. Is this ever 0? No. Is this ever undefined when the function is defined? No. It's undefined at positive and negative 1, and so is the function. So then what can you tell me about the sign of all this? Always? Always positive. So now, if the first row does not match the second row, then we know it'll say, oops, something is wrong. So the function has to be increasing at all times. That's what this derivative says. From 0 to infinity, is it increasing? From negative infinity to 0 to positive infinity, is it increasing? From negative infinity to 0, is it increasing? That's it. So the final step is the second derivative. We determine the symmetry, determine asymptotes, we determine x and y intercepts, we determine increasing, decreasing. We determine that this function doesn't have a max-min. So now we need to identify concavity. And if there is an inflection point. So this is our first derivative. So I'm going to use this and determine the second derivative. So the second derivative. So the top function prime is 2x times x squared minus 2, x squared minus 1 squared minus the top, which is x squared plus 1, times the denominator prime, 2 times x squared minus 1 times 2x. It's very easy to make a mistake here. Let's think about this one more time before we simplify it. So the top function prime is 2x times the denominator minus the top times the denominator prime, 2x squared minus 1 times the inner function prime, which is 2x, over the denominator to the 4th power. If at this stage I do not do something crucial, I'll never finish. And what is that crucial step that I need to perform right now? I have to factor out. What? What will I factor out? So I'll factor out 2x, and I will factor out one of these. So 2x, x squared minus 1. This is an absolute crucial step, because otherwise I will never be able to simplify this function. So 2x comes out from both terms, and x squared minus 1 will come out from both terms. What is left from the first term? And x squared minus 1. Don't forget the minus sign. So this is gone, this is gone. I have 2. I have negative 2 to distribute to these two. Negative 2x squared and minus 2. Yes, now I can do this. So then I have 2x. In here I have negative x squared minus 3. So I'll put a minus outside. X squared plus 3 over x squared minus 1 to the third. So the top will have negative x squared minus 3, and I factor out negative 1. Because I'm getting it ready for setting it equal to 0, so the second derivative, or y double prime, equals 0, results in only x equals 0. So back to the table, I will put 0 here. Okay, now I have to study the sign. And I will prepare it for this sign like this. Because I will not put anything in here. It would be a waste of time. X squared plus 3 and x squared minus 1 squared are always positive. I don't care to plug in anything in there. But I have to be careful here. So, for a number like negative 2, right here, negative with negative, but this is positive. So this must be positive. Careful now, negative 0.5, negative, but this is also negative, because this will be 0.25 minus 1. So negative, negative, negative. With 0.5, negative over negative. And then with 10, negative. Inflection point. So the function has an inflection point at 0. It was expected because it's an odd function, symmetric with respect to the origin. So I'm not surprised at all. I know you are not either. So let's graph this function. I only need the table. I don't care for anything else. I will graph the asymptotes. Negative 1. Positive 1. And there is no need, this is an overkill, there is no need for y equals 0, but because it's already there. So the function opens up from 0 going to infinity. Then the function comes from negative infinity opening up, changes concavity, opening up and going to infinity. No problem, as expected. And then on the other side, from negative infinity to 0, increasing all the time. And this is the function f of x, negative x over x squared minus 1. Any questions here, please?